Hi viewers, this is Sri Ramlu. So before watching this video, please subscribe it. Now today's topic is Davisson and Germer's electron diffraction experiment. See the experimental arrangement consisting a diagram. See the first point. The experimental arrangement is shown in figure, right? The operators consist of an electron gun G where the electrons are produced and obtained in a fine pencil of beam, electronic beam of known velocity. See here, operator consisting of electron gun. So where is the electron gun? So this is the electron gun. So this diagram is electron gun. Okay, gun, it produces electrons and it is coming outside is the electron gun. Okay, and obtained in a fine pencil of electronic beam of known velocity. So let the which velocities come? They are known velocity. Known velocity means some velocity they are coming. Okay, and fine pencil beam means see here the many slit. It is one slit, another slit, another slit, like this. Many slits are there. So by using those slits, what we can get? We can get a small line beam like this. We get. Okay, so why? Because these are generally we call diaphragms or slit. So these can stop electrons which are coming in this direction, and they allow the electron which are moving in this direction, means like this. Okay, to fall on the target. Okay, next point. Electron gun consists of a tungsten filament. See, this is the filament, tungsten filament. Okay, tungsten filament F heated to dull red. So dull red means not bright red. When it comes into light red color, then you have to stop heating. Okay, so that electrons, what happens? Electrons are emitted due to thermionic emission, means due to heat only, due to heat. Next point, this point, the electrons are accelerated in the electric field of known potential difference. See here, we are giving potential difference. See, we are giving potential difference. So potential difference can make electron to move faster. Potential, what it will do? This potential difference, what it will do? This potential difference, it makes the electron to move faster. So faster electrons are called accelerated electrons. That is the meaning of accelerated, right? In the electric field with a known potential difference. Known potential difference means we are how much we are applying, we know here. That is a potential, that potential difference known, called known potential difference. And next, after this electrons are collimated by a suitable slit to obtain a fine. So after producing the electron here, what happened? We are getting a fine beam by using many slits. Here many slits are there to make them to becomes a fine pencil beam. Pencil beam means inside the pencil lead, how it is straight in direction with the small size. The same manner electrons also travels like that, and it strike to the target. Next, the beam of electron is directed to fall on a large single crystals of nickel. See, it is this material is a nickel. It is prepared with the nickel material having large in size. And it is only one piece. It is one single crystal. This is, and this is known as target, denoted by T here. Okay, it is known as target, denoted by T. The next, the electrons acting as a wave and are diffracted in different directions. Okay, electrons when they act as a wave, then they travel in different direction. That is the meaning of this. Next, angular distribution is measured by the electron detector called Faraday cylinder, which is connected to a galvanometer. So, one cylinder is connected to the galvanometer, that is called Faraday cylinder, and Faraday cylinder can act as a electron detector. It detects the electron which are coming towards it. See here diagram once again. Here electrons comes in this direction, and this is what? This is Faraday cylinder, and it is connected to galvanometer. Okay, so galvanometer can show the how much current is passing through it. So it is a graduated circular scale. It is called graduated circular scale. Why it is called graduated? Graduated meaning is a scale which contains the readings, that is a graduated scale. Okay, so that is a graduated scale. And the next point. It is Faraday cylinder can move on a circular graduated scale. Yes, that is yes. Okay, to receive reflected rays. Okay, which rays are reflecting? So those rays will be received by the what? Cylinder. Which cylinder? Faraday cylinder. Okay, just now I have shown. And the next, a retarding potential is maintained between them so that only fast moving electrons coming, sorry for the fast moving electrons, okay, right, sorry for the disturbance. A retarding potential is maintained between them so that only fast moving electrons coming from the electron guns may enter it. What is the meaning here? Retarding potential means decreasing potential. What decreasing potential? The electrons, when the electrons are coming and when they strike to the target, so when they fall on the target, then here few electrons are also generated. So those generated electrons, what their speed, what we have to do? We have to decrease. So if you want to decrease, then what we have to do? We must apply a retarding potential. That is the meaning of this. See in the diagram once again. It is a nickel target T. So here the fast moving electrons coming and they are striking to the nickel target. Okay, so when it strike to the nickel target, then what happens? Nickel target may produce electron. Those electrons are called secondary electrons. So that is also given the points, so I will explain once again. That is, so secondary electrons. So these secondary electrons should not travel fast. Their acceleration must be small. If their acceleration must be small, then what we have to do? We have to apply a retarding potential, right? So a retarding potential we have to apply. Okay, retarding potential. Next, no erasers. Yes. Okay, where we are? It is about okay. It is about retarding, and those and see next point. Secondary electrons produced by the collision with the atoms from the nickel target are reflected by Faraday cylinder. Secondary electron, just now as I told you. So it is a beam of the electron gun, and then they may strike to the nickel target. The nickel target, inside the nickel target, electrons are also produced. Those electrons are called secondary electrons. These secondary electrons are their speed is lower down by the retarding potential. Here it is retarding potential. Then they cannot move fast. Only fast moving electron may reach the sixth cylinder, also given here. Cylinder with cylinder detector. So for fast moving electrons coming from the electron gun may enter into it, and secondary electrons produced by the collision with the atom from the nickel targets are reflected by the Faraday cylinder. So they do not come towards the cylinder, so they move away from the cylinder. Okay. Next, last point is, in this way the galvanometer deflections is only due to electrons coming from the electron gun only. It cannot receive slow electrons, very slow electron it cannot, or secondary electron cannot be received by the detector. So only fast moving electron, means which electrons coming from the electron gun only, those electrons are received by the cylinder, and that electron can show the current in the galvanometer. Okay, and the next procedure. So first of all, the accelerating potential V, generally potential is denoted by V. Potential V is given a low value. So at the beginning what we have to do, we have to give the small value, means slowly we have to increase the potential. Okay, so you know where potential we can change, see the diagram, in the diagram. So in the diagram here only we increase the potential, slowly we have to increase the potential. The next, okay, first of all the accelerating potential is given a low value, and the crystal is set at any arbitrary angle. Crystal means which crystal? Target, nickel target is a single crystal, nickel target is single crystal. So that single crystal is set at any angle. Arbitrary angle means the angle which is changing, or a changeable angle is called arbitrary angle. So we can change the arbitrary angle. And here once again see the diagram, then you can easily understand. See, it is this is the target is set at theta is equals to 50 degree only. Theta is equals to 50 degrees only. It is set. Okay. See clearly. And next coming to point. Now the Faraday cylinder is moved to various position on the scale S, and a galvanometer current is noted for each position. So where we are keeping the cylinder, there how much current is producing, at so and so place how much current is producing on the scale. That current is we must note it. See once again the diagram. It is a cylinder. This is a cylinder. So sorry, it is a circular graduated scale. Suppose at the beginning cylinder is here. Then how much current is produced, that can be denoted by the galvanometer. Next, move your cylinder slowly in this direction at this point. Then also current changes. How much current how much current is flowing through the galvanometer? Take it right on the notes. Next, here like this. At various position, means at a different position, we have to note that different galvanometer current only. Right. The next point is, here it should be remembered that galvanometer current is a measure of intensity of, sorry, no E here, no E, only intensity of diffracted beam. Okay, so what we have to note that galvanometer current indicates intensity of diffracted beam. Okay, and the next, a graph is plotted between, means a graph is drawn between whom? Galvanometer current and angle. See, it is a galvanometer current and angle. So galvanometer current is in this side, and at a 44 potential at different position, we have to draw that graph. Next, the observations are repeated for different accelerating potentials corresponding to curves as shown. So slowly what we have to do, potential we have to increase slowly. First at a 20 degrees Celsius, at 20 volts, theta values at what angle we are calculating, and how much galvanometer current is producing at a different position. Like this, at this voltage we have to calculate and draw a graph. Next, increase the potential 20 to 40. Again increase the potential and do the same thing. Next 44, next 48, next 54, next 60, like this. At a different values of V, we have to, at different values of V, we have to calculate galvanometer current and as well as angle, and at each value draw one graph. So like this, at a different value, at different potential, we get different graphs like this. Okay. Next point. Next, it is a procedure and observations are there. What we observed by this experiment. So it is observed that a bump begins to appear in the curve for 44 volts. So actually bump starts at 44 volts only. It starts at 44 volts only, 44 volts. And see the diagram, at 44 volt. Bumping means what? Bump means here, this is called bump. Alright. And compare the bumps. Here the bumps, here's the small bumps and the bump is increased, and here the bump is increased. This side bump is decreased. So where decreased? Here what potential is there? At 60. Beginning potential is 40. At 44 potential bump starts, and at a 54 potential bump reaches maximum value. At 60, from 54, what happens, gradually bumps starts decreasing. That is the meaning of this. Okay. Next, first point. Here the first point is what? With increasing the potential, bump moves upward. Okay, with increasing potential bump moves upward. So just now I have seen in the diagram. Okay, like this. And here the bump started at 44 volts. Okay, again if you increase voltage 44 to 48, then what happens? Bump gradually increases. This bump value increases, and at a 50 volts bump reaches maximum value. Okay, that is it bump with increasing potential bump moves upward. Okay, next, second point is the bump becomes most prominent in the curve. It reaches the peak value in the curve for what voltage? At 54 volts. At what angle? At theta is equals to 50 degree only. Okay, 54 volts, 50 degree. So don't forget, don't get confusion. Voltage is a 54, angle is 50. Okay, next, at higher potential bumps gradually disappear. So just now I told you, at higher potential means from the 60 volts bump starts slowly decreasing, and beyond 60, at 70, 80, slowly it starts disappearing. Finally you cannot see any bumps. Okay. The bumps in its most prominent state verifies the existence of electron wave. So here in the curve at a 54 voltage, what bumps is maximum? This bumps is because of when electron behaves as a wave, then only this bump create. So they explain in this manner. Who? Davisson and Germer, right? And the next, according to de Broglie wavelength associated with the electron accelerated, when the electron accelerated through the potential V, there is one equation. That equation is what? Lambda is equals 12.26 by root V. This is the root, like this. So it is not clearly here. So this is formula. So bumps a maximum at what? It is most prominent means maximum at what voltage? V is equals to 54 volts. Substitute V value at this point, then what you get? 12 point lambda is equals to 12.26 by under root 54. Then what we get? We get lambda as 1.67 angstroms. 1.67 angstrom. So there is a wavelength. We got the wavelength value in terms of angstrom, means yes, it is exactly correct. Exactly correct. Electrons, when it is moves, it associate a wavelength. Its wavelength already given 1 point. We experimentally they calculated 1.67 angstrom. So that means this can prove that electrons behaves as a wave when they are when it is accelerating. So this is the total experimental details. So thank you friends. Don't forget, once again, don't forget subscribing, commenting and liking.